Okay, here we have a session in R Studio, in fact, and we're going to see how we fit logistic regression models using the GLM functions in R. So the first thing we're going to do is load the ISLR package, which has all the data sets we're going to use. Here we use the command require, which is similar to library. I tend to use require. It's more evocative of what we're doing. And so we just click through in RStudio, and the S-market data set's there, and we can query it. So names is useful for seeing what's on the data frame, and summary is also useful. Summary gives you a simple summary of each of the variables on the S-market data frame. And we see that there's a number of lags, and there's volume, and there's today's price, and there's direction, which we're going to use as a response, and that is whether the market went up or down since the previous day. And we can also do help on these data objects and get some details of each of the variables. And so there you see the description. So we're going to use the direction as a response and see if we can predict it as a binary response using logistic regression. Let's make a plot of our data. So there's the pairs function, and we do it. It's a little bit crowded in this plot. We told it to plot the variables in S-market, and we told it to use as a color indicator actually our binary response. And that's a useful way when you've got a two-class or a class variable for seeing in the plots which are members of each class. And here we see them. It doesn't seem to be too much correlation going on here. Now, of course, the class variable is derived from the variable today, and so up or down, it seems to make a division, right? And other than that, we don't see much going on. Of course, with stock market data, you don't expect to see much going on, because if things were very easy to predict, people would be making lots of money from it, and they wouldn't be giving lectures on using R. So here we have a call to GLM. GLM.fit, we tell it direction is the response, and the predictors we're going to use the lag variables, so that yesterday's price, previous day's price, and so on, up to lag 5, and we'll also use volume. And we tell it to use family equals binomial. And so that tells GLM to fit a logistic regression model instead of one of the many other models that can be fit with GLM. Okay, so we execute that fit. And, oops, I skipped a line here. So there we go. And there it's done. It's 2 lines there. And then we do a summary. And the summary tells you some things about the fit. And in this case, it's given you p-values on each of the coefficients, the estimated coefficients, their standard errors, the z-score, and the p-value. And it seems like none of the coefficients are significant here. Again, not a big surprise for these kinds of data. It doesn't necessarily mean it won't be able to make any kind of reasonable predictions. It just means that possibly these variables are very correlated. Actually, the plot doesn't suggest that. Anyway, none are significant. And it gives the null deviance, which is the deviance just for the mean. So that's the log likelihood if you just use the mean model, and then the deviance for the model with all the predictors in. That's the residual deviance. And there was a very modest change in deviance. It looks like 4 units on how many degrees of freedom. We got 6 degrees of freedom difference in degrees of freedom there. Okay, so we can make predictions from the fitted model, and so we assign to glm.probs the predict of glm.fit, and we tell it type equals response. So this will make predictions on the training data that we use to fit the model, and it gives you a vector of fitted probabilities. We can look at the first 5, and we see they're very close to 50%, which is, again, not too surprising. We don't expect to get strong predictions in this case. So this is a prediction of whether the market's going to be up or down based on the lags and the other predictors. We can turn those probabilities into classifications by thresholding at 0.5, and so we do that by using the if-else command. So if-else takes a vector, in this case glm.probs, in fact a vector of logicals. So glm.probs bigger than 0.5, so that'll be a vector of trues and falses. And then if-else says that element by element, if it's true, you're going to call it up, otherwise you're going to call it down. And so that does that for us. And now we're going to look at our performance. And here it's convenient to actually attach the data frame market so that the variables are available by name, which we do. And now we can make a table of glm.pred, which is our ups and downs from our prediction, against the true direction. So we do that, and we get a table, and we see there's lots of elements on the off-diagonal element, on the off-diagonals. On the diagonals is where we do correct classification, and on the off-diagonals is where we make mistakes. And we see there's quite a lot of those. And we can actually get our mean classification performance. So that's the cases where glm.pred is equal to the direction, and we just take the mean of those, so it'll give you a proportion, in this case 0.52. So on the training data, we do slightly better than chance. Well, we may have overfit on the training data. So what we're going to do now is divide our data up into a training and test set. So what we'll do is we'll make a vector of logicals, and what it is train is equal to year less than 2005. For all those observations for which year is less than 2005, we'll get a true, otherwise we'll get a false. And now we refit our glm.fit, except we say subset equals train, and so it'll use only those observations for which train is true. So now that means we fit just to the data in years less than 2005. And now when we come to predict, we're going to predict on the remaining data, which is years 2005 or greater. And so we use the predict function again. And for the new data, we give it S market, but indexed by not train. So that's going to be not train is going to be true if year is 2005 or more. And we tell it type equals response. So we actually want to predict the probabilities in this case. And again, we make this if-else, make this up-down variable. And let's make a subset, a new variable, direction.2005, again for the test data, which is the response variable, direction, which is just for our test date, in other words, not train. So we call that direction.2005. And now we make a table. So now this is on test data. There's a smaller subset of the data is test. And we compute our mean again, and it's 0.48. So now we've actually gets slightly less than 50%. So we're doing worse than the null rate, which is 50%. So what are we going to do? Well, we might be overfitting, and that's why we're doing worse on the test data. So now we're going to fit a smaller model. So we're going to just use lag 1 and lag 2 and leave out all the other variables. And so here we do that. The rest of the call's the same. And then we run through our commands again. We compute our table. And here we get an error rate of 55. A correct classification of just about 56%, which is not too bad at all. And so using the smaller model appears to have done better here. And if we do a summary of that guy, let's see if anything became significant by using the smaller model, given that it gave us better predictions. And of course, that's what happens when you try and do commands on the type on the fly, at least for me, you make spelling mistakes. Well, nothing became significant, but at least the prediction of performance appeared to have improved. So that's fitting logistic regression models in R using the GLM function and family equals binomial.